Okay, thank you very much to the organizers for inviting me and also for organizing this interesting meeting. I was sitting in the back in many of the talks and I got to hear many interesting things which we don't usually hear. So I don't know how well I fit in this whole meeting, but I just thought I'll talk about some of the work I've been doing on the information paradox, and some of it does relate, I feel, in some ways to issues of the foundations of quantum mechanics. And hopefully that will be of interest to some cross-section of the audience. Before I start, let me just mention some references. So this is work based on some papers we've been writing over the past few years, as you can see over the past 3 years or so. And a lot of it is done in collaboration with Kyriakos Papadimos, who's at CERN and Groningen, Shouvik Banerjee, Jan William Bryan, and Sudeep Ghosh, who's a student at ICTS and in the audience here. These are my collaborators, and I thought I should mention them before we start. I want to talk about the information paradox, and as you can see, this is something we've been thinking about for the past few years. And in fact, I think it's fair to say that our understanding of the information paradox has improved a lot and has sharpened a lot in the past few years, and I'll try and describe how that has come about. And I wanted to describe roughly what some of this sharpening has been about and what we have learned in this process. And so I thought I'll start first of all just by talking about the naive information paradox, or the old information paradox. And then after that, I'll talk about some recent developments, which are about cloning and strong subadditivity. And I'll talk about some of the resolutions, which I think we understand reasonably well, which have to do with what is called black hole complementarity. And in the end, I'll talk about the information paradox in AdS, which is related to this somewhat cryptic phrase in my title called state dependence. And so I'll explain that as we go along. Okay. So let me first tell you what the information paradox is not. So the information paradox is not what often is described to be in the popular media. And the popular description of the information paradox is as follows. It says, think of Hawking radiation, and if you think of Hawking radiation, you can take a black hole and you can form a black hole in many different ways from collapse. Our star could collapse to, our sun, if you made it bigger, could collapse to form a black hole. Some other star could collapse to form a black hole. And there's all this initial information that lives in whatever collapse to form the black hole. But whatever you start with, it always looks like you get out black body radiation. Okay? So you start with our star, or you start with some other star, you form a black hole, and you always get black body radiation. And this looks like a paradox. It looks like a paradox, and this is another way of saying it. You have a small black hole, and this is a rephrasing of the same paradox. Let's throw a library into the small black hole. Library goes in, you get a big black hole. After some time, you have Hawking evaporation, and now you have radiation, and you're back with the same small black hole. So it looked like all the information in the library has been perfectly shredded into radiation, and this looks like a paradox. Okay? But this is not a paradox. Okay? Let me emphasize that this is really not a paradox, because this is just a statement of the thermalization of pure states. It's the statement that if you start with a pure state can have a lot of initial information, but if you allow it to evolve, a pure state thermalizes, by which I mean, if we started with the gas in this room, and if we put it in a pure state so that we broke the entanglement of the gas molecules with everything outside, and then I took this gas in this room, and I put everything to one side of the room. And after some time, the gas would thermalize. Even though it would be in a pure state, it would still thermalize. And it would look like the initial data about where the gas molecules were, in which part of the room they were, was lost. But it's not really lost. This is just the usual seeming irreversibility of thermalization, which is not really irreversibility. There's a way to say this more precisely, which is the statement that if you take a generic pure state, which means you pick a pure state using the Haar measure in the Hilbert space, and you ask how close are expectation values of typical operators in this generic pure state to the microcanonical ensemble, it turns out that they're exponentially close, and there's this deviation of expectation values of an operator in a pure state from the microcanonical trace is suppressed by 1 over the entropy of the subsystem. And this is something which has been known for a long time. One of the places this was phrased precisely was in 1988 by Seth Lloyd in his PhD thesis, but it's a very simple result. And therefore, what this tells us is that the fact that Hawking radiation looks thermal to a good approximation, it's not exactly thermal, does not imply that the final state is a mixed state. All it implies is that the final state is close to being a mixed state, but most pure states are close to being a mixed state. Okay? This doesn't say anything about entropy. This just says that this doesn't say anything about entropy. No, of course not. Or what do you mean by entropy change in the transition? Which entropy are you talking about? This entropy is a dimension of the microcanonical ensemble. This doesn't change. There's a coarse-grained entropy which might change. What? The von Neumann entropy. I mean, there's no von Neumann entropy here because this is not going from a pure state to a mixed state. This is a pure state evolving to a pure state. There's no pure state going to mixed state here. Everything here is completely consistent with unitarity. This is just a trivial statement about the fact that pure states look like mixed states. If I give you expectation values of simple operators in pure states, you cannot use them to distinguish between pure states and mixed states. This is not an appeal to eigenstate thermalization. This is a theorem about averaging over pure state using the Haar measure. This is stronger than eigenstate thermalization. Okay. So there are many ways of saying the same thing I just said. Okay, let me say it in 3 different ways. One of them is that if you had very small corrections of order e to the minus s by 2, these could restore unitarity to Hawking radiation. So if you took the final Hawking radiation formula and you allowed me to add e to the minus s by 2 wherever I wanted, I would get a final formula that was unitary. Here's one more way of saying the same thing. This is something Maldacena said in this language in 2001. Here's another way of saying the same thing. If you give me a pure density matrix, then expectation values of some, for a large class of observables in that pure density matrix are the same as expectation values in a thermal density matrix, and I can arrange these expectation values to be close up to order e to the minus s by 2. Here's a third way of saying the same thing, which is that if you give me a pure density matrix, I can arrange so that the difference of the pure density matrix and a thermal density matrix is down by e to the minus s into a correction matrix where typical matrix elements in this correction matrix are order 1. So there's no magic here. All that's happening here is that you have a very big final state density matrix, and because it's such a large final state density matrix, because the final state density matrix is size e to the s into e to the s, individual matrix elements can be very small, and you can still have something which is pure differ from something which is completely mixed, like this thermal density matrix, by the small correction. Okay? And here's another way to say this in words, which is that information about the initial state can be encoded in tiny correlations between the Hawking quanta. Okay. So this is something which is it's a very simple statement in statistical mechanics, and this is what, if you looked at the naive version of the information paradox, which is that, look, you get Hawking radiation which looks thermal, it's resolved, and there are many ways of saying the same resolution, and here are various ways of saying that. Okay. Let me just say how you'd see this from the path integral. You could ask, where do you see these exponentially small corrections in the path integral? There are many places to see them. In fact, sometimes people say, let's try and improve Hawking's calculation to try and extract information. So let's try and do more orders in perturbation theory. But this is a very difficult task, and that's because if you think of where these exponentially small corrections can come from, you recognize that the path integral itself is a sum over all kinds of metrics. And all perturbative effective field theory is an asymptotic series expansion about a saddle point of the metric, of this path integral. And that's, it's only in that notion of a saddle point that you have a notion of a semi-classical, metric. So a semi-classical metric which has locality is a saddle point of the path integral, and we know that asymptotic series expansions don't give us infinite accuracy. They only give us accuracy up to the next closest saddle point, and the next closest saddle point contributes precisely with terms that are proportional to e to the minus s. Therefore, other saddle points can very easily contribute to restore unitarity, and in various examples like AdS CFT, we do see this happen. So the fact that Hawking radiation looks thermal is not a mystery, and it's very easy to resolve this using exponentially small corrections, and what is more, these small corrections can come from other saddle points. Let me come to Samir Mathur's statement in some time. But yeah. Okay, so right now I'll talk about Mathur in a minute. Okay, so this is just a naive information paradox. Okay? So here are some ways to say the naive information paradox. The statement is Hawking radiation appears to be thermal for different initial states. This is not a mystery. It just happens in pure state thermalization. And then there's one more statement which many people make. In fact, unfortunately, Hawking also makes the statement, which is no mistake has been found in Hawking's computation so far. But that's also not something which is very meaningful because Hawking's computation is not precise enough to lead to a paradox. So there is no question of finding a mistake in Hawking's computation. Hawking's computation as it stands is just not precise enough to lead to a paradox. So if you look at this naive information paradox, which is sometimes phrased in these two ways, it's not really a paradox. It's not really a paradox, and we understand its resolution fairly well. So now you could try and ask, can you sharpen this paradox? And indeed you can sharpen this paradox, coming to what some of the questions were asked now. And let me try and explain how you can sharpen the paradox. So one of the common threads whenever you try and sharpen the paradox is always that you have to make reference to the interior. So remember, note that in what I said previously, I was only talking about the exterior. I was only saying, here's Hawking radiation, we do a computation in effective field theory, we find the Hawking radiation is thermal, and that looks like a paradox. And as I pointed out, that's not really a paradox. But you can sharpen the information paradox, but one thing that's common to all of these sharpenings is that they make reference to the interior. So if you really want to think about the information paradox, you also have to think about the black hole interior, and it's only when you get the black hole interior in place that you can sharpen these versions of the information paradox. So let me explain how that happens. So here's one way to sharpen these versions of the information paradox, and that way is as follows. Okay? So let's think of a black hole, and let's think of a black hole which is evaporating. Okay? So this black hole it was formed from collapse some time back, and then this black hole is now evaporating, so it's emitting Hawking radiation. One heuristic way to think about Hawking radiation is to think of pairs of particles being emitted. So in this pairs of particles being emitted, I'll think of a particle B that's being emitted outside by Hawking radiation, and its partner C, which is falling into the black hole. So we have a pair of Hawking particles that's being emitted, and then there's a collection of the set of Hawking particles that was emitted a long time back, and let's call that collection of Hawking particles A. Okay, so this is just for lack of imagination. I'm going to call these three subsystems A, B, and C. Okay, so A is the set of all the old Hawking quanta. B is the set B is the Hawking quanta that's just being emitted, and C is the partner of the Hawking quanta that's just being emitted, that's falling into the black hole. Okay? So these are three subsystems. Now it turns out we can say some things about these three subsystems. One of the statements we can make is that if we think of this black hole as having been formed from the collapse of a pure state, then we could consider the von Neumann entropy of this system A. Remember, A was the set of all the Hawking quanta that had been emitted up to some time t. If we consider the von Neumann entropy of this system A, then see in the beginning, this von Neumann entropy is 0 because there's nothing in A. So A is basically just a vacuum, and if you subtract off that vacuum contribution, this entropy is just 0. A is empty. If we believe in unitary evolution, which we do, and as I said, it's very easy to make overall unitarity consistent with Hawking radiation, then in the end, S is 0 because it started from 0. So you had a pure state, the pure state went to a pure state. So at the beginning S is 0, and at the end S is 0. But in fact, Page pointed out by doing an analysis of the average entropy of subsystems that in fact you can get to a good approximation the full curve that S forms. And he pointed out that in fact S, this von Neumann entropy, increases monotonically up to some maximum value, and then it decreases monotonically. And this point where it changes from increasing to decreasing is what is called the Page time. Okay, so you have a Page time where the entropy increases and then it decreases. How what? Because you see it's a pure state, so in the end the black hole is completely evaporated. So everything is back to being pure. Everything is in A. Now A is the full system, so therefore it's 0 in the end. And in the beginning A is nothing, A is just a vacuum. In the end everything has come into the Hawking radiation. So if the initial state was pure, the Hawking radiation is pure. That's why A is 0. Okay, good. So now here's this paradox, which was set up in fact by Samir Mathur in 2009, and then popularized by Almeri, Marolf, Polchinski, and Sully, which really formulated by Mathur in 2009. And the paradox is as follows. You see, let's look at an old black hole which is past its Page time. Past its Page time, I'm going to go back in a second, is past this dashed line. Okay, so we are looking at an old black hole on this part of the curve. So if you look at a black hole in this part of the curve, then you see that SAB must be smaller than SA. The reason for this is that, B is the part which is going to go and join A after some time, and therefore A at time t plus delta t is A and B at time t, right? Because B is going and purifying A. All the additional Hawking radiation that's being emitted after the Page time is purifying the old Hawking radiation, and therefore you can prove just on these Page kind of arguments that SAB is smaller than SA. We also know that since the Hawking quanta that are produced, the pairs of Hawking quanta that are produced, that state is related by a Bogoliubov transformation to the vacuum for the infalling observer. We know that SBC is smaller than SC. The fact that individual Hawking quanta are thermal, but the pairs of Hawking quanta together are almost pure, tells us that SBC, which is very close to 0, is much smaller than SC, which is a thermal value. But if you put these two statements together, you see that you're in trouble with what's called the strong subadditivity of the von Neumann entropy, which tells us that SA plus SC has to be smaller than or equal to SAB plus SBC. And that's clearly violated here because SAB is smaller than SA and SBC is smaller than SC. Okay? And remember that this makes reference to the interior because I have to make a reference to the subsystem C, which is the Hawking quanta that's falling inside the black hole. And what is more, it looks like this is a violation at order 1. It's not some small violation that you can fix, but in fact it's a violation which looks like it's some order 1 violation of strong subadditivity of entropy. So it looks like a sharper version of the information paradox in the previous one that we outlined. This is in fact closely related to an older paradox which was called the cloning paradox. So the cloning paradox went as follows. It said, think of a black hole in flat space which is formed by the collapse of some shell of matter, and then in the shell of matter we can quantize the system on these so-called nice slices. And so this blue slice is what's called a nice slice, and you can choose these nice slices to tilt up, to hug the horizon for a long time, and then go and meet a spatial infinity. And if you do that and you use the same page argument that I mentioned, then it looks like these nice slices can collect a lot of the outgoing Hawking quanta, remember, which comes out of this black line, which is the horizon, and meets this blue slice at these red points. So the nice slices can collect a lot of the outgoing Hawking quanta, and so they can collect a lot of the information, but the same information is also present on the nice slice as part of the infalling matter. Because the classical solution tells us the infalling matter is still there, while there is the quantum analysis tells us that Hawking radiation is going out in this way. So this is what's called a cloning paradox, because it tells us the same information is there on this red point, x in, as it is on these red points, x out. It's here because of the Hawking radiation, which is carrying the information out, and it's here because of the infalling matter, which had the information in the first place. And of course, cloning is in violation of the linearity of quantum mechanics, and therefore this is another version of information paradox, which once again I point out makes reference to the interior. It's not a paradox that's framed purely in the exterior, it makes reference to the interior, and it looks like, again, it's something with small corrections will find hard to resolve. Okay, so these are two sharper versions of the information paradox. So the way to resolve these paradoxes is through a version of what's called black hole complementarity. In this setup, what black hole complementarity means is that we say that if there's some local field that lives at this point x in, then we identify the local degrees of freedom at the point x in with a very complicated polynomial, that's what this P stands for, of the local degrees of freedom outside. So the claim is that the degrees of freedom inside the black hole are really identified with the degrees of freedom outside the black hole. So black hole complementarity is a statement that as operators, these are not distinct degrees of freedom. It's not that these degrees of freedom happen to have the same expectation values in some states, but really that these are really the same degrees of freedom. And you can see that that resolves entirely the cloning paradox, because now what's happening is not cloning, but rather that you happen to be really measuring the same degrees of freedom at x in as you're measuring at x out. Now, let me just say before I say a little bit more, you might object to this immediately, because you might say, our world is approximately local. We know that degrees of freedom in my right hand are not the same as degrees of freedom in my left hand. Clearly, they're distinct degrees of freedom. So how can it be that you identify one set of degrees of freedom with another set of degrees of freedom on the same space-like slice? But this is okay, provided you ensure that the commutator between two degrees of freedom which are space-like separated vanishes inside correlation functions, provided these correlation functions are not very high point correlation functions. And I'll say in a minute what I mean by very high point. But let me just try and point out that complementarity violates locality, but it violates locality in a very subtle way. It doesn't violate locality so as to be inconsistent with any observation that we have in our everyday life. What it says is that there is some commutator, and that commutator is non-zero, but to see the fact that it's non-zero, you have to do some very high point correlation function calculation, or you have to measure something to exponential accuracy, Otherwise, you don't see the non-zero commutator. So there's a non-zero commutator, and that non-zero commutator is very hard to see, but it exists. Okay, so that's the kind of statement that we want to make from complementarity. And as I said, this ensures that there's no violation of quantum mechanics, but instead says that there's a subtle loss of locality. I'll give you an example of how complementarity works more precisely in a few minutes, but let me just point out how complementarity resolves not only the cloning paradox, but also the strong subadditivity paradox. You see, the point is that if you look at these three subsystems, which we use to set up the strong subadditivity paradox, the system of old radiation A, the system B, and the system C, if complementarity is true, and it's really the case that the Hilbert space inside the black hole is a scrambled version of the Hilbert space outside, so that a relation of this form holds, then these three subsystems are not independent. And one of the assumptions you make in proving strong subadditivity is that the three systems you're considering are independent subsystems. The first statement is that the Hilbert space factorizes into HA, tensor HB, tensor HC. And if for some reason that's not true in the theory of quantum gravity, then there's no strong subadditivity paradox to set up. So complementarity resolves not only the cloning paradox in an obvious way, but also the strong subadditivity paradox by denying the factorization of the Hilbert space into the space outside and the space inside the black hole. Okay, so I'm going to go on and explain how complementarity works in one specific example. And that's because, you might ask me, you might say, okay, that's a good idea, but why should I believe you? Why should I believe that there is this kind of loss of locality? And so to show that this is something that we can check in specific examples, I want to give you a specific example from just empty anti-de Sitter space. So one setup where we think we understand quantum gravity very well is in AdS CFT, and just in empty anti-de Sitter space, which is a setup where we really think we understand quantum gravity well, I want to show you how complementarity can be realized in a very precise way, not with any approximate symbols, but really as an equation. And I want to show you how, in precisely the sense I mentioned earlier, that there is a loss of locality, there's a non-zero commutator, but it's a commutator which is very hard to see and realize complementarity. Dispersion. No, you're modifying microcausality, you're not modifying the dispersion relation. Microcausality, yes. Okay. So let me just try and point out what I'm going to show you. In fact, I know that many people in this room don't work on AdS CFT. So what I'm going to say, in fact, doesn't rely on too much of AdS CFT. So even if you don't work on AdS CFT, I'll try and explain it in a way that you should still be able to follow. It really relies only on canonical gravity, what I'll say right now. So what I want to do is, here's AdS. So anti-de Sitter space, you should think of as a solid cylinder. Okay, so one good way to think of anti-de Sitter space is to think of anti-de Sitter space as a solid cylinder. There's a boundary of this solid cylinder, which is this boundary, and in this boundary there's some object here, which is in the center of AdS. And I've drawn the causal diamond that completes some band here about this red circle, which is this diamond D, and then there's this region D bar, which is spatially separated from all points inside this diamond in the middle. Okay? So the geometry is very simple, and what I'm going to show you is how an operator in the middle of AdS in this D can be written as a combination of operators inside D bar. Okay, that's what I'm going to show you. And as I said, there's nothing deep happening here. In fact, the only reason I need anti-de Sitter space is because I want an infrared cutoff. Okay, so let me try and show you how the argument goes. I won't go through all the details, but I'm happy to explain them more if people have questions. The first statement is that there's some set of states you get in anti-de Sitter space just by doing quantum field theory and curved spacetime. So if you do quantum field theory and curved spacetime, you get some complete set of states, and let's call those states n. Okay? That's just some basis of states. By definition, this operator in this diamond D in the middle of AdS has some expansion in terms of this complete set of states with some coefficients C and M, and these coefficients are such that this operator gives you an approximately local field. This is just coming from doing standard quantum field theory in curved spacetime about anti-de Sitter space, which does give you local fields, and it does give you an expansion of local fields in terms of the set of states in the theory, which is this. So there's nothing controversial here. Second, you can in fact use a version of what's called the Riechschneider theorem So I don't know how many of you are familiar with the Right-relational theorem, but let me just tell you what it says colloquially. What the Right-relational theorem tells you is that if you give me the set of all local operators in a compact region, in fact, by acting on with only those local operators, I can create a space which is dense in the full Hilbert space of the system. And this is not a violation of locality. This is the statement that if you give me the set of all local operators in this room, by acting with those local operators, I can create the moon in Alpha Centauri. And this is just a statement in ordinary quantum field theory. It's called the Right-relational theorem. I can prove it to you if you like, but it's just a, it's not a violation of locality. It's a well-known statement in quantum field theory. There's a slight generalization we have to prove here, but the fact is that these states n can be created by taking a simple polynomial in the operators phi of d bar and acting on them on the vacuum. So this x is a simple polynomial. It's a simple polynomial of operators which are all spatially separated, and they act on it and they act on the vacuum, and you can create these states in this way. So far, what I've said is true in any quantum field theory. There's no violation of locality that's going on here. Okay. But now we find the following. You see, in this setup, I was able to get the states n, but that's not enough to get the operator in terms of polynomials in d bar. To get the operator, what I need to do is I need to get this projector on the vacuum which sits in the middle of those states. And you can get this projector on the vacuum, in fact, by realizing it as a limit of e to the minus alpha h, where h is the Hamiltonian of the theory. And this e to the minus alpha h, you can realize, of course, as a high enough polynomial in the Hamiltonian of the theory, just by expanding out this exponential and taking alpha to be large enough. So if you take alpha to be large enough and just expand this exponential out to some suitably high cutoff, I'll tell you what that cutoff has to be in a minute, then you can get this polynomial, which is the projector on the vacuum, you can get this operator as a very complicated operator in the Hamiltonian. But remember that in gravity, and only in gravity, not in any ordinary quantum field theory, the Hamiltonian is an operator on the boundary. But the boundary is entirely contained in this region d bar, which is entirely spatially separated from d. So we see that this projector on the vacuum can be written as a very complicated polynomial in d bar, all of which is spatially separated from d. How complicated does this have to be? It has to be complicated enough to ensure that, well, there's some cutoffs that come from the infrared and UV cutoffs in AdS. Let me not mention, I can explain these cutoffs in more detail. Let me just tell you that if you take this alpha to be roughly log of the AdS scale by the Planck scale, which is log of the cosmological constant in natural units, and if you take this cutoff to be AdS scale or the Planck scale into this log, then this gives you a suitably accurate approximation to the projector, the vacuum. And therefore, you see, by combining the fact that the Right-relational theorem allowed you to get operators, allowed you to get states, in states by acting with simple polynomials in d bar, and the fact that the gravity Hamiltonian is a boundary operator, and therefore allowed you to get the projector on the vacuum as a complicated enough polynomial, we see that we can write this full operator in terms of, simple polynomials in d bar and complicated polynomials in d bar. So this is this is really a formula. I haven't given you all the details, but you can really look up this formula. It's really a formula that explicitly realizes this version of complementarity. It says that an operator in the middle of anti-de Sitter space can really be equated with operators that are all spatially separated from the original operator. But of course, to come up with an equation of this kind, you have to use some very complicated polynomial in the operators that are spatially separated. How complicated does it have to be? I argue that it has to have an order which is at least cosmological constant in Planck units. Okay? And this is really an equation, and it does give you something which has which satisfies the criteria I mentioned earlier, which is that first of all it gives you this equation, and secondly it's consistent with approximate locality. Okay? Now we don't have a real realization of complementarity in flat space, but we do have strong indications that something like this should be true. The reason it's harder to realize a formula like this in flat space is because we don't have a good IR cutoff in flat space, which we do have in anti-de Sitter space. But there are strong indications that something like this should be true, because as we, in a recent paper with Sudeep, we showed that, in fact, if you look at string perturbation theory, and you look at string perturbation theory with many external particles, even if they have very low energies, then string perturbation theory breaks down. This is a sign, the fact, looking at an S matrix with many low energy particles is roughly the same as looking at a correlation function with lots of smeared operators. And the breakdown of perturbation theory in gravity, as I pointed out earlier, has to do with the breakdown of the saddle point approximation, which has to do with the breakdown of locality. So this is giving us a hint that space-time locality breaks down if we probe space-time at too many points. I can try and make precise what too many means if there are questions about this, but that's precisely a statement I made in anti-de Sitter space. I could try and make this statement precise in flat space as well. Now this doesn't directly lead to a realization of complementarity in flat space, but it gives a hint that a similar formula should hold in flat space as well. Okay. So far I've talked about versions of the information paradox in flat space, and I pointed out that we have a pretty good understanding of how to resolve the information paradox if you just talk about the outside. We also have a reasonable understanding about what the correct direction is if you talk about more sophisticated versions of the information paradox, such as the strong subadditivity or the cloning paradox. I think that the information paradox really becomes very sharp when you start talking about anti-de Sitter space and you start talking about big black holes in anti-de Sitter space. And I'll try and explain some of the interesting phenomena that come about when you do that. So this is in fact a long story on which a lot of papers have been written, and I won't have time to review the whole story here. But roughly speaking, the statement is that if you try to understand the black hole interior in anti-de Sitter space for big black holes holographically, then you end up with a large set of paradoxes. And the reason I'm calling them the information paradox, even though they don't really have to do with loss of information as the flat space paradoxes did, is because they also rely on a conflict between unitarity and effective field theory. So I'll try and explain a little bit in detail how that happens in one specific example, but there's a vast literature in this, which again I'm happy to go into if there are questions, but I won't go into otherwise. Okay, so let me give you one example of how this happens. So one setup in AdS CFT which we understand pretty well is what's called the eternal black hole. So the eternal AdS black hole is a black hole which has a Penrose diagram of this kind. So there's a singularity in the past, there's a singularity in the future, there's a future horizon and a past horizon, and this eternal black hole has two boundaries. Okay, so unlike just empty anti-de Sitter space that I showed you earlier, this has a left asymptotic boundary and a right asymptotic boundary. And it is believed, and there's a fair amount of evidence for the statement, that this eternal black hole geometry is dual to what's called an entangled thermofield state of two conformal field theories. So it's not dual to a state in one conformal field theory, but it's dual to a state in two conformal field theories, and it's dual to a particular state which has this kind of entanglement between two CFTs, and this is called the thermofield state. Okay, so now if you look at this thermofield state, what I want to do is I want to consider some time-shifted thermofield states, where I take this thermofield state and I evolve it with the Hamiltonian of the left CFT. If I do that, I add some phases to this thermofield state. These phases are nothing but the energy into this time, a modulo, of course, 2 pi. Okay? And so I add some phases to this thermofield state. But we have a geometric understanding of what evolving with the left Hamiltonian is. We have an understanding of the CFT, of course, where it just adds these phases. But geometrically, evolution with the Hamiltonian, it's well understood in all analyses of quantum gravity, corresponds to large diffeomorphisms. What does a Hamiltonian, evolution with the Hamiltonian do? It does a large diffeomorphism which does not vanish at the boundary. Right? So in particular, e to the IHLT, evolution with the left Hamiltonian, corresponds to doing a large diffeomorphism that dies off at the right boundary, but not at the left boundary. That's why it's evolution with the left Hamiltonian. Okay? This is a very robust statement. So for example, one way of thinking of such a diffeomorphism could be a diffeomorphism that moves a nice slice of this kind to a nice slice of this kind. This would be a diffeomorphism that would take the red slice to the blue slice. But of course, there is no unique diffeomorphism that does this. I could write down a formula for this diffeomorphism in terms of the Kruskal U and V coordinates, but there's no unique diffeomorphism that does this. That's because all diffeomorphisms, large diffeomorphisms that differ by trivial diffeomorphisms are equivalent. Trivial diffeomorphisms are those that die off at both boundaries. So here's one more picture of the diffeomorphism, which is one where it acts just infinitesimally close to the boundary. Okay? So it doesn't act on bulk points at all, but it just slides the left boundary up and down. So in fact, the way you should think of this e to the IHLT operation in the bulk is one as just, which leaves the bulk geometry invariant, but just changes the way the boundary of the space is glued to the space. So that's a good gauge invariant way of thinking about this diffeomorphism. Okay, so now I want to talk also a little bit about some good gauge invariant observables you can talk about in the bulk. The gauge invariant observables I want to talk about are what are called right-relational observables. When I start with the right boundary, not the left boundary, but the right boundary, and I jump in from the right boundary, I send some light rays back to the boundary to normalize my affine parameter. But roughly speaking, you can think of it as an observer who jumps from the right boundary, who waits for a certain proper time, crosses the horizon of the eternal black hole, and then makes a measurement. This kind of an observable is invariant under diffeomorphisms that don't reach the right boundary. It does vary covariantly with diffeomorphisms that reach the right boundary, but doesn't vary with diffeomorphisms that touch only the left boundary, like the diffeomorphism I talked about previously. Okay? So now, let's look at these observables, these right-relational observables, in this family of states, which are the original Thermofield state, all shifted with these phases. Because the geometric understanding of these phases is produced by acting with left diffeomorphisms, you see that these right-relational observables should be such that they should give you the same correlation functions in all these different states. Remember, the physical answers obtained by someone who's measuring a right-relational observable should be the same in all of these states. Therefore, the correlation functions of the right-relational observables should be the same in all of these different states. When the observer crosses this horizon, he does observe excitations from the left, but if this observer is supposed to get the same results in all of these states, that must mean that in this state psi of t, the right relational observable corresponds to some left observable, but shifted by this amount t. So in fact, I may have lost some of you, so let me just summarize the whole thing once again in 2 lines. You see, I have a family of states. I have a family of states which is the original geometry, plus a whole bunch of geometries with large diffeomorphisms done in the left bound. These diffeomorphisms don't affect a right relational observable which is framed to the right. Therefore, in the quantum theory, all correlation functions of these right relational observables should be the same in all such states. Therefore, you see, because these observables, these right relational observables, do depend on operators in the left theory, they must be operators in the left theory shifted by this amount t, so that it cancels off this original t. I can make this relation a little more precise, but you see that these are the observables, so that if you sandwich them in this state, they'll give you the same answers as the original observable in the Thermofield state. Okay, that's obvious, because this plus t just undoes this e to the IHLT. So I've done an inverse Heisenberg evolution compared to this evolution I've done in the state. Okay? But, this is not the way you specify observables in any quantum theory. You don't say, you give me the state and I'll give you the observable. You give me the observable ahead of time once and for all. So the prescription I did right now is what's called a state-dependent prescription of the observable. I said if an observer jumps in the state that corresponds to this state, then this observer should use these observables to determine his physical results. But that's a state-dependent prescription. In fact, it turns out that you can't do better. There is no state-independent observable that automatically reduces to these shifted observables in this entire family of states. So I won't give you the proof of this statement. Again, I'm happy to describe in more detail if you want. But let me just try and intuitively tell you why this is happening. Why intrinsically it turns out that you have to use state-dependent observers. The reason is as follows. One way to think of all of these states with large diffeomorphisms done on the left is to think of states which have, which are some solutions of the equations of motion. You see, all of these states correspond to solutions of the equations of motion where the boundary is glued differently to the bulk in each case. Every solution of the equations of motion corresponds to a point in the phase space of gravity. That solutions to the equations of motion are always in one-to-one correspondence with points in the phase space. Now, usually, you see, what happens is, if you tell me how an operator behaves at a certain point in the phase space, I can lift that to some operator on the full Hilbert space. So in particular, if I told you in general, in a general theory, that an operator behaves, has this form, for every solution, then I could use coherent state quantization to construct an operator on the full phase space that started behaving correctly whenever I sandwiched it inside a particular coherent state. Okay? So usually the way that works is we do coherent state quantization, just a couple of minutes, where we start with some function in the phase space, we have some set of coherent states, we do this kind of an integral, we get an operator. This operator automatically behaves like the function f of z if you reinsert it in the coherent state z. Okay? But this in fact relies on a particular behavior of the norm on coherent states. And the norm on coherent states dies off exponentially with distance. And that's why coherent state quantization works. Now in this setup, where we have a full theory of quantum gravity, you can in fact compute the norm between these different coherent states. So you can compute the norm between the state with no shift and the state with shift t. And in fact this norm does turn out to die off exponentially for small shifts, but for large shifts this norm has a fat tail. So this norm, these states which correspond to coherent states don't quite have the same inner product that coherent states would have had. So if you think of the semi-classical inner product is this blue curve, and it dies off faster than this exact inner product which has a fat tail. And that's what prevents you from lifting these functions on the phase space to some good state independent observables in the full Hilbert space. And I can explain this in more detail again if there are questions. So the final picture we get as follows. You see, we get a large subset of states in the full Hilbert space which are labeled by this one parameter t. This is the original Thermofield state which has t equal to 0, and this space goes off to very large values of t on both sides. And the set of operators that we get to define interior operators in this geometry, we have to work patchwise in this Hilbert space. So given a particular state, time shifted state psi of t, I can define operators that give me the correct correlation functions in the neighborhood of that state in the Hilbert space. But I have no way, and you can prove that there is no way to extend these observables to good observables in the full Hilbert space. Okay? In fact, if you move too far away from your initial state, you need to switch to new operators. So this is what I mean by state-dependent operators. They're operators which are good in a neighborhood of Hilbert space, and they're not operators that are good everywhere in Hilbert space. Okay, so I'm done. Let me just give you a slogan. See, one slogan why you need state dependence is because coherent states are always overcomplete, but the set of coherent states that are dual to geometries in AdS-CFT are even more overcomplete than one would expect from a semi-classical analysis. Coherent states are always overcomplete, but these states are even more overcomplete. Okay, good. So let me just say something which may be of interest to people here. You see, if this statement is correct, then it's a very interesting statement because it requires us to really reevaluate our theory of measurement. See, we don't usually, the way we talk about measurements is by means of a von Neumann protocol, and then by using the coherence theory to say that some observables become classical. But here, in holography, and in fact in any notion of cosmology, local observables are emergent. They're not things you add to the Hamiltonian. And therefore it's possible that they could be state dependent, but if so, we really need a good understanding of how to measure local observables in cosmology and holography, which can't be via the von Neumann protocol, especially if they're state dependent. Okay, so that's all I wanted to say. Let me just conclude with this summary slide. Let me just summarize what I said. As I said, there's a naive information paradox, which is the statement that Hawking radiation is universal, independent of the initial state. This is not really a paradox. It's just reflective of pure state thermalization. There are sharper versions of the information paradox in flat space that come by looking at cloning and strong subadditivity. These are the statements that somehow information appears both outside and inside the black hole simultaneously, but we have a reasonably well understanding of how we should resolve them by means of black hole complementarity, which we understand very precisely in anti-de Sitter space, not so well in flat space, but we have some good hints that something like this should be true. And then we have paradoxes that have to do with the black hole interior and anti-de Sitter space. What these paradoxes tell us is that interior operators must be state dependent. If that's the case, that's something very new about observables in quantum gravity, and we would like to understand that better. Okay, so I'll stop here.
So we have some time for questions. So any question? Okay.
So I don't really understand how you resolve this, the second line there, but I missed that part of the talk, so I won't ask about it. Let me ask about the second. You claim that you believe that it's perfectly consistent to have unitary evolution for the region outside the black hole, I suppose, in an evaporating black hole scenario. Is that what you're claiming?
This is correct. I can explain more. Is that the question?
No, that's not the question, because I didn't hear your argument for it. I'm just skeptical of it, but we can just talk later.
Okay, I did explain it, but go on. Yeah. What's the question? I can answer.
The question part that I did hear, why is it not, I mean, you ended up saying, in this particular summary, you said interior operators must be state dependent. In your earlier slides, you said right-hand operators must be state dependent.
I said
operators that pertain to the right side of the right boundary or something, or
so
the right half of the. Yeah.
I understand. Yeah. Let me answer your first question first.
No, but I haven't asked a question.
Oh.
Oh, yeah, I mean, you can, let me answer the first question second if you want. But why is it not just totally obvious that the interior operators have to be state dependent? Because whether there's a black hole there at all is state dependent. So what would it even mean to define an interior operator in a state independent manner?
So I don't know what to say to that. The statement that's completely obvious is, this is the kind of statement where sometimes you hear people saying it's either completely obvious or it's totally crazy. You see, if it's, what it would mean to define an operator which was state independent, it would be to write down some operator in the Hilbert space that happened to have the correct correlation functions when you sandwiched it inside a black hole state, but happened to have some meaningless correlators if you took it in some other state. But if you sandwiched it in any state which did have a black hole there, it would automatically have the correct correlation function. Let me give you an example. For example, you might say there's a phonon operator on this table. When I hit the table, I excite a phonon operator. Now you might say, what does it even mean to talk about a state-independent phonon operator? Because the statement that there is a phonon excitation presupposes the presence of the table. The way you get around that is by putting a projector onto the table. So you write down an operator which says O, sorry, I'm being very schematic here, a little comic, but which says the table exists, and you multiply it with the correct operator, and then you don't care about what happens if the table doesn't exist. So this is a state-independent operator that happens to have the correct correlation functions whenever the table does exist, and you don't care about what it does when the table doesn't exist. So what you would mean to write down some operator which would describe the interior in the presence of the black hole would mean that you would write down an operator that went of this kind, where Pi was a projector onto the set of all microstates which had a black hole geometry. So you would write down an operator which had this form, so that, where this was a projector onto all black hole states, and this would be a state-independent description. And what I'm pointing out here is that in a description of this kind doesn't work. It's not obvious that it wouldn't work, but it doesn't work indeed. Let me answer your question about complementarity. The statement was that you have these paradoxes that have to do with here's one you might be familiar with. This is called the cloning paradox. It's a statement that if you think about these nice slices, then if you have infalling matter, the infalling matter intersects the nice slice in the interior. The nice slice can hug the horizon and can go up, so it can capture a large amount of the Hawking radiation. So it looks like you have the same information inside and outside. The proposed resolution to this is that you identify the degrees of freedom inside with a very complicated polynomial of degrees of freedom outside, which violates locality in a subtle way but doesn't violate quantum mechanics. And the evidence for this is that you can actually realize this as a formula, which I explained here, very precisely in anti-de Sitter space. You take anti-de Sitter space in the absence of a black hole, and you can write an operator in the middle of anti-de Sitter space as a very complicated polynomials of operators which are all uniformly spatially separated.
Okay, so I'm not convinced that, or let me put another. If you do this, then you're going beyond quantum field theory and curved space.
Yes, you're going beyond quantum field theory.
Because you're making some identification of states that would have been distinct in quantum field theory and curved space-time. Is that a fair statement?
To some extent, although in this really arises from the Gauss law constraint. This is really taking the Gauss law constraint and pushing it. Even in quantum field theory and curved space, if you compute Dirac brackets, there's a Gauss law constraint that prevents you from having exactly zero commutators in gravity. It's true that to really write down this formula, we need a version of AdS CFT to make it precise. We need, we basically need, the statement you need is that the projector onto the vacuum can be approximated as some very complicated polynomial of the Hamiltonian, and the Hamiltonian is something you can realize at the boundary. Now, it's true that to make the statement very precisely, you would need AdS CFT, but you would also have had the statement in canonical gravity. Even in canonical gravity, the Hamiltonian would be a boundary term, and this is just promoting the Gauss law constraint to something which requires this kind of identification. So it's using, in fact, a combination of the Gauss law constraint and the Riesz-Leiter theorem. So if you combine the Gauss law constraint
Riesz-Leiter theorem is something for flat space quantum field theory.
Correct. So the Riesz-Leiter theorem does involve
background quantum field theory.
Yes, I said that. So you weren't here for this part of the talk.
No, I told you. That's why I didn't ask the question.
Theorem is indeed something which doesn't violate locality. It's something which would work for a theory which satisfies microcausality. So I don't want to go through this whole thing again, but you use the Riesz-Leiter theorem. So you take this operator in the middle and you write it in terms of a complete set of states. Then you use the Riesz-Leiter theorem to write each state in terms of a simple polynomial of operators which are spatially separated. So far, this is consistent with microcausality and holds in any quantum field theory. Then you also realize the projector on the vacuum has a very complicated polynomial of the Hamiltonian, which is only true in quantum gravity. It's not true otherwise. So you use this fact, which is only true in quantum gravity, with something which is true in every quantum field theory, to realize, the full operator in terms of a projector in the vacuum and something else you get from Riesz-Leiter. So there is something here which is special to gravity, but there's something which is not, which is Riesz-Leiter, and then there's something which is special to gravity, which is that the Hamiltonian is a boundary term.
So would you say that, I don't know if I should keep asking questions, but would you say that naive calculations of, say, entanglement entropy or the entropy of the Hawking radiation are just wrong? That really, we have the state description given to us by the semi-classical treatment, which ought to be, I mean, either you're saying that it's fundamentally changed, or you're saying we can't even use that language to talk about the external state.
So I think
that would be a little disturbing,
gravity,
because then
that's right.
we wouldn't understand the generalized second law.
No, so I think in the presence of gravity, it's clear that we don't have a good understanding of how the Hilbert space factorizes. I don't think we have a good definition. I think we barely have a good definition of entanglement entropy in gauge theories, if you think about that carefully enough. But in the presence of gravity, we really don't have a good definition of entanglement entropy. Now, entanglement entropy happens to be a very fine-grained observable. If you just look at correlation functions, they give you a good diagnostic of locality, which indeed you can preserve. So it's good to demand that correlation functions should approximately commute at space-like separation. But it's not good to demand precise properties from entanglement entropy, because indeed we do not understand that how the Hilbert space factorizes in theories of gravity. So I would say that if you're going to take entanglement,
I was thinking more of the sort of the Hawking quanta, which are entangled nominally with quanta that are inside the black hole. So this has to do with entropy of the radiation field. It could be quite far from the black hole.
Indeed,
it's not particularly an ultraviolet issue in that case.
No, but it's not really this is not, this kind of identification is not an ultraviolet issue. It's a statement that there's a fundamental loss of factorization in the Hilbert space between the region outside the black hole and the region inside the black hole. So you take a nice slice that cuts through the horizon, and there's a loss of factorization, which in fact you can see very precisely in an empty anti-de Sitter space. So you can just take empty anti-de Sitter space in AdS CFT, and you can set up a version of this exact same strong subadditivity paradox just here. In fact, by imitating a horizon, by restricting yourself to a finite time band. So this is something which in systems which we understand very well, you can see the precise same kinds of paradoxes arise if you start taking entanglement entropy and theories of gravity too seriously. So it's not just a speculation about black holes. In this example, we do happen to understand it very well that this is what happens.
Okay.
We can talk more if, yeah.
Yeah, please. If there are other questions, please catch hold of the speaker after the session.